Metal redistribution process. Okay, so what does this actually mean? Redistribution process means to form a new shape with a material that can be turned from a solid to a liquid. The new shape uses the majority of the material. Not much material is wasted depending on the process that is used. Have we covered this before? The answer is yes and no. We have covered metal-based forming processes, which we did about 2 terms ago, and Mr. Thompson has covered some of this area but not in great depth, which is why we're going to go over it again today. To help you reflect on what we've covered before, there is a starter practice quiz on Show My Homework. You can take the quiz without revising first to see what you actually remember. There's images that you need to label, etc. So it's not just all questions and answers. So have a go, and you can take it at least 3 times. So maybe take it without revision first, go back, look at your notes, complete some revision, and then give it another go. Let's look at what we'll actually be looking at for this session. So for this session, we're going to be covering the following processes: sand casting, which you may have seen before, die casting, investment casting, and low temperature pewter casting. And we're going to start off with sand casting. So these are some products that have been made using the sand casting process. So sand casting is primarily used with high melting point metals. They are used in one-off or batch production, and this is because the molds are one use. So once the mold has been used, it's made out of sand, and the mold must be destroyed in order to get the product. So that is why primarily it is used in one-off or batch production, as it can become quite time-consuming to repeat the mold making process. Because sand is used, it does leave a grainy texture on the product, so you won't get a fine, beautiful finish. So here is a process of what sand casting looks like, and I'm just going to briefly talk through the 6 stages. So stage 1 shows you something called a drag. So the drag is the first part of the mold, and the orange blob at the bottom, that's called the half pattern. So the pattern is the actual the mold shape that you're trying to reproduce, and it has to be cut in half. So the first thing that will happen is the half pattern will be flat-sided down at the bottom of the drag, and then a release agent will be applied in the form of a powder. Okay, so that has to go right over the pattern, because eventually this pattern needs to be removed, and we want it to be removed easily and safely without damaging our mold. Once the release agent is applied, sand is then filled to the top of the drag, and as it's being filled, it's filled in layers, and then each layer is compressed. So it's very, very dense, it's very heavy, and it's very, very secure. And then as it gets all the way to the top, the excess sand is then strickled off with a strickling rod, and all that means is the top is being leveled. And let's go on to number 2. So 2 shows you the second part of the mold, which is called a cope. Now, for those of you who are observant, you can see that the drag has actually been flipped upside down. So now when you look into the drag, you can see the half pattern, the flat side, and the bottom of the sand. So the cope is placed on top using some location pins to make sure that it's accurate and that the walls meet beautifully. And the second, and before the second part of the pattern is applied, a releasing agent again must be applied to the mold and to the sand already. These 2 pieces will eventually be taken apart before the molten metal is applied. So the releasing agent must be added before the second half of the pattern, and the sprue pins are then put in place, which is what I'll come on to now. So the second half of the pattern is then applied, and then we put in some sprue pins. So these sprue pins will be used as a pouring basin and as a riser, and I will explain what those mean in further detail as we go through, but basically it means that one will be where the molten metal is poured into, the other is where the molten metal will rise from. Now once these are securely put in place, again more sand will be added, which you can see in option 3, And again, it will be compressed as each layer is added because you want it to be really, really compact, really, really secure. And then if we go down to number 4, here you can see that the two parts have been separated and that the pattern and the sprues have been removed, okay? So everything in white there, that's all vacant. So when the two molds are compressed together and pinned in place, which you can see in number 5, you can see where the pouring basin and the riser is on the left and the right, and you can also see that some vents have been added. So these vents make sure that any trapped air can escape, and this reduces the likelihood of any bubbles happening inside or on the outside of the mold when you eventually remove it. So once these two, once the drag and the cope are securely pinned in place, and the molten metal is ready to go. If you look at number 6, you can see that the molten metal is being poured into the pouring basin. And as it flows through, it will fill the cavity, the mold cavity, so where it was blank, where it's empty, it will fill that. It may ever so slightly rise into the vents, ever so slightly, depending on how narrow they were made. And they will pour up into the riser. So when the riser is full, that indicates that the mold is full and hopefully that the process has been successful. So that was sand casting, and this is a quick revision overview that you can use for your own resources. So the PowerPoint is on Show My Homework also, so you can print this off or you can use it to make your own revision resource. Okay, so let's move on to die casting. So these are some products of die casting. You can see we've got a doorknob, a lock, a golf club, figurines, alloy wheels, and toy cars. So this shows you that this process can be used for a variety of different products. Some products that might have really refined, accurate little details like the figurines, and some products that might just be quite a basic shape but with little fiddly, complex inner pieces such as the lock. So die casting uses low melting point metals such as aluminium and any alloys of aluminium and zinc. The process uses tool steel molds that are reusable and extremely strong, so they could be used hundreds of times without showing wear or damage, which is why they're used in mass and large batch production, as the molds are complex and expensive to make, so they want to get their money's worth out of them. They do produce very accurate products with very high quality surface finishes as well, and die cast products can also be chrome plated, as they have such a lovely fine surface. They can take the chrome beautifully and you can end up with an even higher quality looking product. So there are different types of die casting, and the first one we're going to look at is gravity die casting. So the overview and the products made with the process is the same as what we've discussed before, but it's the process itself that's a little bit different to others. So if we have a look at the image in the top right hand corner, you can see that there is a mold, okay, a die cast mold, and it has a runner and it has a riser. So this is extremely similar to the sand casting. The runner is where the molten metal is poured into, and the riser is where you can see it rising up as it is filled to capacity. Again, like with sand casting, if you look on the right hand side, you can see that the mold has location pins. This means that they can be placed accurately together so that there will be no defects in your overall product. Before the two molds are pressed together or formed together, they must be sprayed with a lubrication or some kind of releasing agent so that the finished cast can easily be removed from the mold. Without this, it would be extremely difficult and you could cause damage to your mold trying to remove it. When the casting process is finished, because it is molten metal, obviously it will need some time to cool, so a cooling agent can also be applied. So this is just a jet of cold water that will run over the mold to help cool down the product inside so that it could be released effectively and efficiently and fairly quickly. Okay, so here's a diagram that shows you the hot chamber pressure die casting. Now, there are some similarities to the gravity die cast process I showed you earlier, but there are quite a few differences. Let's start by looking at the die itself. So you can see here that the die contains a number of ejector pins. In this example, it has a core which will create a void within the product. And then the die is made in two parts, an ejector die and the cover die. Now the difference being the cover die does not move. It remains in the same place throughout the process. The ejector die, however, will be pulled back once the product is cooled down. The other really big difference is the molten metal and the placement of it. So in hot chamber pressure die casting, the hot metal, or molten metal, sorry, is kept in a chamber which is attached to the die. And you can see it is attached here through a nozzle and something called a gooseneck. Okay, and this is where the molten metal will travel. So let's talk about how the process actually works. So within the chamber here, you can see that we have an inlet and we have a plunger. Now the plunger, which will either be a pneumonic or a hydraulic run plunger, will rise up, allowing molten metal to gather into the gooseneck chamber via the inlet, which is here. Once it is filled to capacity, the plunger will then drop down at a significant force, which will create a shot of molten metal, which will travel through the gooseneck, through the nozzle, and into the die itself. Now, just like with the gravity die casting, the die would have been covered with some form of lubrication or releasing agent. Okay, that has to happen in order for the product to be removed later on from the die. Now, once the molten metal is shot through, it will then be kept in place at a high pressure via the plunger. The plunger will stay down and it will not be released back up until the product itself has cooled down to an appropriate temperature for when it can be handled or released safely. So here is an example as to how the ejector die removes itself. And you can see that any leftover molten metal has stayed within the gooseneck and partly into the nozzle, and that the core has also been removed, which creates this void in the product. Now let's go back to these ejector pins, because what will happen is the ejector pins will then push the product out of the mold, which is why it must be well lubricated with some form of releasing agent. And then the product itself, it will either fall into a container or it will just fall onto a conveyor belt where it will then go on and be processed. It may also be just simply dropped on the floor where it will then be picked up and have a chrome finish applied to it. But the molten metal will continue to sit here in its chamber and it will be reheated and reliquidized to complete the process over and over again. So here is another overview as to what the hot chamber pressure die casting process is, what it looks like, and again the products that it is used to make. These products will be the same as the gravity chamber die casting. However, you could probably notice that perhaps that doorknobs and door handles, these are what would probably be made on mass production, as they are a requirement that we need in our homes, so they are in huge demand for the construction industry and building trade. This is the final area of die casting that we're going to look at, and this is cold chamber pressure die casting. So from the diagram, I'm sure you can see some similarities compared to the hot chamber pressure die casting we just looked at. Our die comes in two parts. We have the ejector die and the cover die. So it's the exact same as a hot chamber. The cover die is fixed in position, whereas the ejector die will be pulled away in order to release the mold from the cavity. We also have ejector pins, which again push out the product from the die releases it into a container or a conveyor belt, etc. And then we also here have a core, just like our other example. And the purpose of this core is to create a void in the cavity so that there will be a void in the final product. This process is really similar to hot chamber in regards to the preparation of the dye. The dye must be sprayed with some form of releasing agent or lubricant, again, so that the product can come away from the dye really nice and easily. The biggest difference, however, is the molten metal is not attached via a chamber to the dye. The molten metal is actually kept in a separate furnace called a crucible furnace. And this is where the metal ingots, so the metal bars, will be placed inside the crucible furnace and will be heated until it is molten. Once it is molten, it will then be travelled or carried from the furnace to the cold chamber via a ladle. And the ladle can be carried by man, or it can be a systematic ladle, depending on the manufacturers. But the molten metal is then poured into the chamber, so it fills up this chamber here. And then when it is filled to the correct capacity, the plunger will then plunge forward at high velocity, forcing the molten metal to fill the empty cavity within the die. Cold chamber pressure die casting is a really good manufacturing method to use to make 2 or more parts at one time. So there'll be 2 separate parts within the die which are filled at the exact same time. Once the plunger reaches the end, it will stay there, keeping it in at high pressure, and after a suitable amount of time has passed and the inside product is cooled, it will then be released, and eventually the ejector die will separate itself from the cover die and the ejector pins will push out the final product. Let's just summarize the differences between the hot chamber and the cold chamber die casting processes. Now, there is a really big, obvious difference. Hot chamber has the chamber of molten metal attached to the die. Cold chamber doesn't. It's heated in a separate furnace and travelled to the die. But what about the metals? The other really big difference between these two processes is the fact that hot chamber uses low melting point metals, whereas cold chamber uses high melting point metals. That's because the furnace that is used to heat up this metal is huge. If you had that furnace too close to the hot chamber die, it would cause damage to the die and to the chambers. It's just too hot. So it has to be transferred from the furnace to the cold chamber, which helps to cool it down ever so slightly, but not enough for it to actually cause damage. But if you think about it, in order to keep this stuff molten, the furnace has to be on for long periods of time, which for hot chamber processes, the metal is pretty much molten all the time whilst that die is being used, because it can be used for mass production. So if you have something that is causing an incredible amount of heat for a long period of time, eventually there will be some damage caused to the machinery. So now that's cleared up. This again is a little revision resource for you for cold chamber pressure die casting. It has our diagram, but it also has our overview that helps to explain the process and the metals that are used. So again, one of the biggest changes in regards to cold chamber compared to hot chamber is that it is used with high melting point metals such as aluminium, or alloys such as brass and copper. And again, at the bottom, you can still see that the products made with this process are still the same as all the previous die casting methods, because the manufacturing process is accurate and can create really high quality finished products. The next metal redistribution process we're going to talk about is investment casting. So here on the screen you can see a variety of images of products that have been made via the investment casting process. We have intricate jewellery, a pump cover, hip joints, collectible figurine, and a turbine wheel. So let's learn a little bit more information about investment casting. So investment casting is also known as lost wax casting. This is because the pattern that is used for this casting process is made out of wax, and it is eventually melted away. It is used to create products with intricate details that would be impossible to achieve using other casting methods. So if you need a very, very beautiful, exact replica of something, you would use investment casting to create that product. It works with a wide range of materials, or metals rather, such as aluminium, stainless steel, brass, and carbon steels. And it utilizes a pattern with the same details as the finished part, except that there is an allowance for thermal contraction, so it will shrink ever so slightly. And it is also minimizes waste. It also minimizes the use of energy and the additional machining that might be used for other processes. So now I'm going to take you through the process. Apologies that the image is a little bit pixelated. I did my best to find a decent diagram. So the first thing that happens first is the pattern needs to be made. So the pattern is the replica of the final product that you want to create. And the pattern is often made using wax or some form of plastic, and it's normally made using the die cast method. So here you can see the injection of the pattern here, and then the final wax pattern outcome. So once all the patterns are made, this is where the tree is then assembled. So here you can see we've got lots of our wax patterns, and the green area here, this is known as the tree. So this is made out of wax, and this is the sprue where the molten metal will eventually be poured. In order to attach the patterns to the tree, additional wax and some heat is used, essentially like a glue or like an adhesive, to bond the two pieces together. The wax pattern and tree is then dipped into a slurry, and this slurry is a liquid ceramic or clay slurry, and it's also known as refractory clay. And as it is dipped into the slurry coating, it is often on an axle which will rotate it 360 degrees, and it will make sure that the whole wax piece is covered evenly. It will then lift the wax out of the slurry coating. It will be left to dry, and once it is dry, it will then go back into the slurry coating to give it another layer. And this happens multiple times until the correct thickness is achieved. Once the ceramic is the correct thickness for the metal that is intended to be used, the wax inside is then melted away. This is achieved by placing the ceramic into a heated chamber, and the wax will eventually melt away and remove itself by keeping the sprue side down so that it has an exit for the wax to run away from. Once it is completely emptied of the wax, the ceramic will then be kiln fired. This will strengthen the ceramic and ensure it is hardened enough for the molten metal to then be poured in, which you can see is happening here. Once the metal is fully cooled, and it will be given plenty of time to cool down, the ceramic layer then needs to be removed, and obviously it needs to be broken. So this can happen just by simply gently tapping it with a tool to break it away. It can also happen through blasting, so high pressure air is blasted onto the ceramic so it cracks and falls off. It could also be removed via vibrations. But you can see in this little diagram, we've got the perfect pattern of our casting. It is almost an exact replica, and that is the process that is used for investment casting. So here is an overview of the process that we've just talked through, so you can see each step side by side. Just in case you're wondering, step 5, which I didn't go through, is stucco coating. Stucco is just a form of plaster which can be applied after the slurry. Again, you would apply the stucco coating depending on the type of metal and how strong you want your mould to be. And here is our revision card for investment casting. There's a different diagram for you for the process, just so you can see it in a different way. It contains our overview and products that are made using this process. So again, it's used to create really intricate, fine, detailed products that you want an exact replica of. So that could be jewellery, medical applications such as hip joints or knee joints, collectible figures, pump cases and turbines. Low temperature pewter casting. I've really enjoyed making these videos, so I thought I'm going to share the fun with you. Your task is to create an instructional video similar to what you've just seen for low temperature pewter casting. Now, if you don't have time to do a full video, please don't worry. It can be a PowerPoint presentation, but you'll get extra brownie points if you manage to actually make a video. If you have your textbooks with you, you can find the information on low temperature pewter casting on pages 63 and 64. And attached to your Show My Homework post, there is also a PDF that contains some information links and images that can also help you. Good luck and have fun!